The power versus load curve can be separated in three zones: a safe operating range, a maximum operating range, and an overload range. The safe operating range is usually between 20% and 35% of the mill volumetric load. Below this range, the mill liners will be severely damaged due to grinding media impact on an uncushioned liner. Above this range, depending on mill design, the level may be high enough that rocks can get caught between the mill feed chute and the trunnion liner. In this range, both the power and load increase and decrease at the same time. The maximum operating range is typically between 35% and 40% of the mill volumetric load. In this range, both the power and load increase and decrease at the same time, but an overload is never far away. The overload range is characterized by a power drop combined with a load increase, or, during recovery, a power increase with a load decrease. From this it is apparent that overload detection is usually based on the rate of change of power and load. If the rate is in opposite direction for power and load, then there is an overload. It is possible to construct a decision table based on power and load. This example is based on a target power and bearing pressure. If both are on target, obviously there are no changes to effect. If the load is above target and the power is on or above target, then the water is increased. This has the effect of producing a coarser mill discharge, and it will reduce the mill contents. If power is below target, then there is the potential of a mill overload. The tonnage is reduced or stopped depending on how low the power is. If the load is very high and the power is on target, it means that the ore is hard to grind. The solution is to add balls. If the power is high, then the feed should be decreased as we approach an overload. If the power is low, then the feed should be stopped as we reach an overload. If the load is low and the power is on target or high, then water is decreased to increase retention time in the mill. If power is low, that means that the mill is underloaded and tonnage should be increased. If the load is very low, then tonnage should be increased to avoid liner damage. It is possible to automate the decision table. This example shows two possible options. In the first, the power controller sends a set point to the load controller, which in turn sends a tonnage set point. If the power is low, the load is increased by increasing tonnage. This works until an overload develops. At that point, the power controller responds to a low power by increasing the load when the load decrease is required. There must be a mechanism to switch off the power controller in case of overload. This is illustrated in the second option. The power controls the tonnage unless an overload occurs, in which case the load controller takes over to correct the situation. This scheme works unless there are ore changes which require different power and load targets. As this plot shows, maximum throughput does not always coincide with maximum power. The rule seems to be that to maximize tonnage, power should be maximized for hard ores and power should be kept to a minimum for soft ores. Intermediate ores show that intermediate power maximize tonnage. A smart control strategy would take into consideration the ore type being processed in order to determine the power set point. It is also possible to take advantage of speed in variable speed mills. The impact is somewhat limited, but it can be advantageously used to compensate for liner wear or for extreme ore conditions. Speed can be combined with sound measurements to minimize liner wear by reducing impacts directly on the liner. However, sound level is a function of feed size, ball charge and mill density, as well as volumetric loading, limiting its usefulness.